Okay, in this next section, your text introduces something called a potentiometer. In a previous chapter, although they said that I believe they mentioned a potentiometer here, I think in the previous chapter it was a rheostat. Go ahead and look up the definition. Go online and look up the definition of the difference between a potentiometer and a rheostat. Each of them has a different functionality. But in this case, with the potentiometer, what they're looking at here is showing you that you've got a resistor with a wiper blade on it. And typically, this is a wire wound resistor, and you've got a pole that moves along the wire wound and adjusts the resistance accordingly. So you can see here when the center pole is set at exactly the center point, you in essence have an amount of resistance. In this case, it could be an equal amount of resistance on each side. So as the wiper is moved, the wiper is exactly centered, making two resistances equal. If you measure the voltage across 3 to 2, as indicated by the voltage symbol, you will have 1/2 of the voltage. So you'll be using these in your lab for measuring variable resistances and setting variable voltages for a voltage divider. So this actually shows you if you connected a meter to 3 and set the pole so that it moved from one end up to the other. You can see how in the center you've got half the voltage. At the far end you've got almost all of the voltage. At the other end you've got less voltage. So it's an adjustable resistor. The applications here, your volume control on any of your audio devices. Turning the knob actually moves the wiper along a resistor. Typically when you turn a volume control knob that hasn't been used for a while or has been set in one place, you'll hear a crackling sound. That crackling sound is because you have some corrosion or something, some buildup on the winds of the resistor or the plates that it's moving along. And so sometimes when you move the dial back and forth, you can wear a path through the wiper arm. Sometimes you can spray the potentiometer with a cleaner and get it to stop doing that. In this case, they show you the operation of a float, where the float itself operates the potentiometer and changes the resistive element, changing the voltage supply. In applications where we use solid state, you can see here we set up a voltage divider that really just sets the bias on the transistor, something you're going to learn about later. The voltage divider then is used as a bias circuit for the transistor amplifier when the voltage at the base terminal of the transistor is determined by the voltage divider R1 and R2. In this case, we've got a little example. Assume that you have a CDS cell configured as shown. So you've got basically a photocell here, and it's setting up the bias or the voltage divider in this cases. That uses 3 AA batteries for the voltage source to deliver 4.5 volts. At dusk, the resistance of the cell rises from a low resistance to above 90 k ohms. The cell then is used to trigger a logic circuit that will turn the lights on if V out is greater than approximately 1.5 volts. So this is typically what you have in a light sensitive device that turns your lights on and off, say your driveway lights or your porch light. What value of resistance will produce an output voltage of 1.5 volts when the cell resistance is 90 k ohms? So in this case, notice that the threshold voltage is 1.5 volts, 1/3 of the supply value. You know that 90 k ohms represents 1/3 of the total resistance at this point. So they're getting you used to thinking of circuits this way. Therefore, the total resistance, our total then is 3 times 90k or 270 k ohms. The resistance value needed to produce the voltage out at 1.5 volts then is R is equal to the total resistance minus 90. So the total resistance we calculated at 320 minus 90 gives us 100 and 180 k ohms. Okay, so we've looked at several configurations of voltage dividers. You're going to see a lot of voltage dividers in your studies in engineering technology for electronics. Looking at back to power again, we noticed that power can be a sum of all the devices that are using up energy in a circuit. So we can go back to our power formulas. Remember, we have three representations, the top one being I times E, or Vs times I, and then the variations based upon I squared R and V squared RT. So if we look at an example here, determine the total amount of power in this circuit. So we've got 1, 2, 3, 4 resistors. And in this example, all we're going to do is determine what the power dissipated on each of those resistors is. So the first thing we need to find out is what the total resistance is so that we can determine the voltage drops on each one. So the total resistance becomes the sum, or 106 ohms. With that information, then the easiest formula to start with then is V squared over RT, since we know both the source voltage and now RT. So we come up with, by applying V squared RT, of 2.12 watts. So that's the total power consumed or dissipated by all four of those resistors. Now, knowing that, we can go back then and look at what the current is in this circuit. So the total current is equal to source voltage divided by total resistance, or 142 milliamps. So we know in a series circuit, the current through one is the current through all. So we can calculate then the power through each of the resistors as I squared R. So 142 milliamps in each of these squared multiplied times the value of the resistance. So the 10 ohm gives us a 200 milliwatt power dissipation. 18 ohm, 360 milliwatts of power dissipated. 56 gives us 1.12 watts. And the 22 ohm gives us 441 milliwatts. Then we can add all of those powers together, dissipation, and when we sum them, we come up with 2.12 watts total power dissipated for that circuit. This result then compares to the total power as determined by the previous V squared RT. Okay, so we can see that they do in fact match. So different ways to solve for power in a circuit. The same thing here. Determine if the indicated power rating of 1/2 watt for each resistor is sufficient to handle the actual power. And this is, a real world thing. You put a resistor in here that has a power rating too small, you're going to smoke it. Okay, so if a rating is not adequate, specify the required rating. So again, we start with finding the total resistance, 7.91 k ohms, then calculate the total current based on the 120 volt source, and 7.91 k ohms gives us 15 milliamps through that circuit. So now we can apply that again to I squared R for each of them. 225 milliamps for one, 608 milliwatts for two, 205 milliwatts for three, 740 milliwatts for four. So R2 and R3 do not have a sufficient rating to handle the actual power. Okay, how do we know that? Well, we go back and it says that the indicated power rating on each one of these is 1/2 watt. In this case, R2 and R3 exceed the 1/2 watt that each of the resistors have. They may burn up if you apply power then, especially during a surge. These resistors then must be replaced with 1 watt resistors. So number 2 and number 4 have the incorrect power rating. Okay, so we've looked at some voltage divider applications and some power calculations. In the rest of your text, they're going through and giving you some information about doing test equipment connections. Go ahead and read through those and take a look at their suggestions here for measuring voltages, in this case with respect to ground. Understanding positive and negative voltage and polarity is important. and then making measurements on a breadboard. Okay, so if you take a look at this, you can take a look at this last sample problem here. So that is all of Chapter 5, finishing up the voltage divider and the power relationships and a little bit on handling test equipment.